Alright, so today we're going to do something quite different. We're going to talk about something called Kepler's Laws. Kepler's Laws are something that will help explain how orbits work. So in other words, how the planets go around the sun, or how moons go around different planets, or how satellites go around the Earth. And it's totally different again than anything we've done so far. But let me show you. First things first, here's today's plan. We're going to talk really quickly about bank curves from last class. I'll explain how to do those again. I'll give you a little bit of a story time about two really bizarre astronomers to kind of lay the groundwork for what we're going to do today. We're going to learn about Kepler's laws of planetary motion, just like Newton's laws. There's 3 of them, so we'll talk about each one. And then we'll have some practice time. So for some quick bank curves review, I'm just going to let you pause the video here so you can write this down. Suppose you're shaping a banked curve on a road so that even if a car takes the curve at 130 kilometers an hour with no friction, that they can still make the turn. The radius of the turn needs to be 285 meters. At what angle are you going to slope the road at? If you remember from last class, there is always one formula that we use with these over and over again, and that's tan theta equals v squared over r times g, where theta is the angle of the road, v is the maximum speed you can go on that road, r is the radius of the turn, and g, of course, is the gravitational field strength. So we're looking for the angle in this case. So we're going to be looking for theta. We just changed colors for some reason. Oh well. We're looking for theta in this case. We know what our velocity is. It's just in kilometers an hour though, so we'll have to change that before we start. We know the radius of the road, and we're looking for theta, of course, right? And gravitational field strength is always given to us. So before we begin again, we want to have common units here. So we need to change these kilometers per hour into meters per second. You might remember that the quick shortcut for doing that is just to divide by 3.6. If you go 130 divided by 3.6, you're going to get that to be 36.1111 meters per second. So this instead is going to be the number that we put into this formula here. So again, we'll say tan theta equals our velocity, which is 36.1111 squared, divided by our radius, which is 285. Times by gravity, which is 9.81. This is going to give me tan theta equals 0.46641. And then, of course, since we're looking for theta, we just have to take the inverse tan on both sides. So if I take the inverse tan on both sides, that'll give me my final answer, which I'm going to round to 3 sig digs, and that's going to be 25.0 degrees. So just like I mentioned last class, with these kinds of bank curve problems, you just reuse the same formula over and over again, and it just becomes an exercise of algebra. Okay, so I'm just going to introduce 2 really bizarre astronomers to you, just to lay down the groundwork for what we're doing today. The first one, and there's 2 different ways of pronouncing his name, Tycho Brahe, that'd be this guy. Some people pronounce that Tycho Brahe. Like I know my university professor would always call him Tycho Brahe, but I looked it up afterwards. It totally is Tycho Brahe, which not to mention I think actually sounds better because it's like Tycho Brahe. Anyway, sorry for that. Anyway, Johannes Kepler is the other one. Johannes Kepler is the guy here on the right. Now, Johannes Kepler was actually Tycho Brahe's assistant. Okay. Now, both of these people, they lived in about the 1500s and early 1600s, I suppose. And they were astronomers that were trying to figure out planetary motion. Now, Tycho Brahe has an interesting story behind him. You might even be able to tell by his picture here. He kind of had a little bizarre nose, right? His nose was really strange, and there's a reason for that. When he was 20 years old, when he was in university, him and another classmate or associate or colleague or whatever got in a fight as to who was the better mathematician. And they literally got so heated with this argument, they went behind like the building they were at or whatever. I think they were at a party when this happened, and they had a fight, like a duel. And during the duel, he took a sword slash right across his nose, chopped the bridge of his nose off, and then he had to wear a prosthetic brass nose for the rest of his life. So this guy, needless to say, was kind of an oddball, right? Now, Johannes Kepler, again, was his assistant. And Johannes Kepler, after Tycho Brahe passed away, Johannes Kepler took a lot of Tycho Brahe's data and was able to construct something that we call Keplers Laws. It really explained how planetary motion works. It explains how the planets orbit around the sun, and it was quite revolutionary for the time. So what we're going to do today is we're going to take his ideas and we're going to run with them. Okay, so today, again, we're going to talk about Kepler's laws. I'll give you a chance just to pause and write this down. Johannes Kepler used Tycho Brahe's astronomical data to create Kepler's laws of planetary motion. These three laws describe the motion of objects in orbit, particularly the orbits of the planets around the sun. It doesn't have to be the orbits of planets around the sun. You can also use this to explain how satellites go around the Earth, or how the moon goes around the Earth, or how any of the moons of other planets go around those planets. Kepler's law is all about objects in orbit, and orbit is, of course, caused by gravity. So Kepler's first law, I'll just give you a chance to write this down. All planets in the solar system have elliptical orbits with the sun at one focus. Elliptical is the key word here. Prior to Kepler, people believed that the orbits were actually circular. And that includes Nicholas Copernicus, who was the one who came up with the idea that the sun was actually the center of our solar system and the planets orbit around it. Kepler, however, figured out that the orbits are elliptical and the sun shows up at one of the focuses. Now, a focus, of course, is basically just the central point of orbit. You don't need to know that term focus, but it would be useful because I know it comes up a little later on. Okay, Kepler's second law now. Again, we'll pause just so you can write this down. Kepler's second law is a little bit beefier than Kepler's first law. Kepler's second law says that over equal lengths of time, a line from the sun to the planet sweeps out equal areas, right? Little bit bizarre. Let me explain. This image that I've got here is very exaggerated, but it's done so just to show a point, right? So there is not actually the case where the sun is that close to us in January and that far away from us in July. It doesn't exactly work like that. It's not that elliptical. But it does illustrate the point that from, let's say, December to January, the area that sweeps through is actually the same as any of the other areas for any other equal amount of time. Now, this picture is also making the assumption that all the months are the same length, but we can just ignore that and assume that every month has about 30 days. But over the same amount of time, the area that it sweeps through, so including this one here, or even like something random like this one, I'm going too wide, this one right here, more or less you get the idea no matter how bad I draw this on here, they sweep over equal areas. That's basically what I'm trying to get at. Now, the entire purpose that this is showing, or the entire reason that this is something noteworthy, is in order for it to sweep through different areas, what this is really saying is the closer the object is to the thing causing gravity, so in other words, the closer Earth is to the sun, the faster it's going to go. Notice in a month, if you just think about the linear, or I guess curved distance that it travels a lot further in this month than it did, say, between July and August, if this picture were accurate, right? However, even though that this distance is less than this distance, this area that it sweeps through, that's a little bit better than I did before. There we go. This area that it sweeps through is the same as the area in this month. That's all Kepler's law is saying, or Kepler's second law, rather, I should say. All right, now Kepler's third law, this is a very heavy slide, so I'm going to give you a lot of time to write it down, so please pause and write the whole thing down. Okay, Kepler's third law is the most important of all three for you to know. And unfortunately, this formula that you wrote down right in the center of the page is not on your formula sheet either. It is another thing, just like the bank curves formula, that unfortunately you are going to have to remember. Kepler's third law says the ratio of a planet's orbital period squared, so the orbital period squared, over its orbital radius cubed, is a constant. All objects orbiting the same focus, whether that focus is the sun, a planet, etc., will have the same constant. And we'll call that constant a capital K. In other words, if something is orbiting around the sun, the constant, where it's the orbital period squared divided by the orbital radius cubed, will be the same for another object. We can call the other object object B. So if you had, for instance, Mercury orbiting around the sun, so we'll say here's the sun, and we have Mercury out here, Mercury we'll say, orbiting around the sun here, the time it takes for it to complete one orbit, in other words, the period, capital T, if you squared that and divided it by the radius of its orbit cubed, that would be the exact same number as if you took, let's say, this is awful, the next planet out, Venus, and took its time it takes to go around the sun, so its orbital period t, squared it and divided it by its orbital radius, right? Bad picture aside, you still get the idea, hopefully. All it means is that there is a constant number that is equal to the orbital period squared divided by the orbital radius cubed of literally any object that's orbiting around that central focus, right? So K is your Kepler constant for that focus of orbit. So whether that focus is the sun has a Kepler constant that is always the same. Whether it's the Earth, so in other words, like the moon going around the Earth or satellites going around the Earth, no matter what object is orbiting around the Earth, you can find a Kepler constant for Earth that is the same for literally all of those objects. Every single satellite, the moon, anything else, etc. T, of course, is the period. That just means how long it takes to make one full orbit. And R is the average orbital radius. It's important to note average because, like I mentioned earlier, these orbits aren't perfect circles. They're ellipses. So there's times where we're closer to the thing causing the orbit, and there are times where we're further away from that object, that focus, I should say. R is just the average, right? And that's always what I'll give you. I'll always give you that average orbital radius, or you'll be expected to find the average orbital radius given every other piece of information. Now, one last thing that's really important to note at the very bottom here is, generally speaking, we like having T in seconds and R in meters, just so it's consistent with every other use that we have for this. But Kepler's third law is kind of neat in that since it's just an equal ratio of two exact same fractions on both sides of this equal sign, you can use any units you like. You just have to make sure you're consistent. In other words, if you said for your capital T, if you said that was in days on the left side of your equation, you got to make sure it's in days on the right side of your equation. Or if R was, I don't know, kilometers, then you got to make sure it's in kilometers on the right side of the equation as well. So as long as you're being consistent, you can use whatever units you like. You just have to keep the left side and the right side the same. Okay, so again, let's pause right here. I'll let you jot this down. All right, so we're going to get some practice finding Kepler's constant. And this time it's going to be for the Earth if the moon is orbiting the Earth once every 27.32 days at an average distance between the cores of 3.844 times 10 to the 8 meters. Now again, Kepler's constant for the Earth would be the same whether it's the moon orbiting Earth, a satellite orbiting Earth, the space station orbiting Earth, anything orbiting Earth is going to have the exact same Kepler's constant here. And again, Kepler's constant, capital K, is T squared divided by R cubed. We know what T is here. It takes 27.32 days for the moon to orbit around Earth once. And we know the orbital radius is 3.844 times 10 to the 8 meters. And it was nice that it told us it was between the cores, because that really is officially how you need to measure this orbital radius. It has to be from the center of the Earth to the center of whatever is orbiting Earth. So in this case, to the center of the moon. So since all this information was given to you, you don't actually need to worry about changing your units because it didn't ask for Kepler's constant in any particular unit. That means you literally can just leave this in days and in meters. And if this was given to you instead of in meters, if I gave you it in kilometers, you could have just left it in kilometers as well. So this is going to become T squared, so that's 27.32 squared, oops, 32 squared, there you go, divided by R cubed, so 3.844 times 10 to the 8, close bracket, and then cube it. If we just calculate this, that's going to tell us our Kepler constant. So it's just as quick and easy as putting this in your calculator. Just be really careful with your brackets. Make sure you put brackets around this stuff, especially the one on the bottom. Anyway, K is going to equal, I got 1.314, that's 4 sig digs, times 10 to the negative 23. That's a 3. Let me erase that. Try it again. 23. And we got to be careful with units here. Units don't matter, but we still need to account for them. Since this top was in days and this bottom was here in meters, and we squared the days and we cubed the meters, our units are just going to be a really bizarre days squared over meters cubed. It's always, always, always needed when you finish writing your Kepler's constant to express what units they were in, so that if someone were to stumble upon this Kepler constant for Earth, they could reuse it to find some other information about any other orbit. Okay, so here's another example. Just pause and write this one down. So this question is saying, use Kepler's constant for the Earth to calculate the orbital period for the International Space Station, which orbits Earth at an altitude of 300 kilometers. So this question again is saying, use Kepler's constant for Earth. That's what we just calculated in the last question, so I can just start by saying K equals 1.314 times 10 to the negative 23, and that was in days squared per meter cubed. So that'll be really useful. Now, we're looking for the orbital period of the International Space Station. We know that K equals T squared over R cubed. The orbital period is, of course, T, so we're looking for T. R cubed is the orbital radius between two things. This question is a little bit of a trick question in that it gave us the altitude as being 300 kilometers, but the altitude, if here is the Earth and here is the space station, the altitude just shows us how far above it is above the surface of the Earth. We don't want to use that. We need to use the distance from the center of our space station to the center of Earth. So we actually need to add that altitude to the radius of Earth. Now the good news is the radius of Earth is actually listed on your formula sheet. So if you wanted to find our radius in this case, it's going to be the radius of the Earth, which again on your formula sheet is 6.37 times 10 to the 6 meters, plus 300 kilometers, which in order to match with the meters here, we should change that to meters really quick. 300 kilometers is just 300,000 meters. If you add those two together, you're going to find that our orbital radius in this case is going to be 667,000 meters, or in other words, 6,670,000 meters. Now that we have all this information, we can plug it in to find our T. So in other words, we can write K is 1.314 times 10 to the negative 23, and that'll equal T squared over R, which we just found was 667,000 cubed. To get T squared all by itself, we just need times by this orbital radius here on both sides. What that's going to give me is a really uncomfortable number. T squared equals, so 1.314 times 10 to the negative 23 times 667,000 to the power 3. This gives me 0.0038991,763. I kept as many decimals here as possible because I want my answer to be as exact as possible before we get to our final answer here. To get to that final answer, we just need to square root both sides. Square rooting both sides here is going to give me 0.0624. And if you remember back what our units were on our Kepler constant, we can figure that this T is actually going to be in days. That is our 3 sig digs we need, so that is a perfectly acceptable answer. But for some people, that might just look a little bizarre. So maybe you want to actually change that into a unit that's not quite as big as days, so it becomes a little bit more realistic. Because if I said something was 0.0624 days, you might not really know what I'm talking about there. As much as this is an acceptable answer, again, some people like having it better, or a little easier to communicate, I should say, by timesing this by 24 to turn it into hours. So if I times this by 24, you're actually going to find it's a much more comfortable 1.50 hours. And believe it or not, you can look this up in your own time. That's actually accurate. So even though really all we ever used was how high the International Space Station was orbiting at, and then just a bunch of random information about the moon on the last question, we were able to accurately find how long it takes the International Space Station to orbit around Earth. So Kepler's information, even though it came out hundreds of years before we ever sent satellites up into space, it does prove to be pretty accurate. All right, so we're going to do one more example here. So just pause so you can write this one down. The length of time it takes Earth to rotate around the Sun is 365 days. It does this with an average orbital radius of 1.00 AU. That means astronomical unit. In case you're not aware, an astronomical unit is the average distance between the Earth and the Sun. It's just something they use to measure distances in space. One astronomical AU, or one astronomical unit, I should say, is 1.49 times 10 to the 9 kilometers, in case you were wondering. Saturn has been observed to have an orbital period of 10,759 days. What is the orbital radius of Saturn in AU? So we're looking for the orbital radius of Saturn. It's asking us to use AU, so that means we should be using this number in our calculations rather than this number in kilometers. We won't necessarily need this. This is where we use Kepler's constant, but we actually string two formulas together, like I showed you when I actually had that slide going. Remember, the Kepler's constant for any object that has things orbiting around it is the same no matter what object you're focusing on looking around, orbiting around it. So in other words, the orbital period of Earth, which is 365 days, that's Earth's t, divided by its orbital radius cubed, so again, t squared divided by r cubed, is going to equal the same number as if you took the orbital period of Saturn and squared it and divided by the orbital radius cubed of Saturn. More formally, we can write this as t of, we'll say, e, that's the period of Earth squared, divided by the orbital radius, r, for Earth, cubed, will equal the orbital period of Saturn squared, so ts squared, divided by the orbital radius of Saturn cubed, right? So this way we actually bypass finding directly what Kepler's constant is for the Sun, because that's the object both of these things are orbiting around, and we just string two fractions together to help us find that information. So we can just fill this in. As long as we make sure we have matching units, we're going to be totally okay. Just filling in all this information here, the orbital period of Earth is 365 days, so 365 squared, divided by the orbital radius of Earth cubed. Because we want the orbital radius of Saturn in AU, we need to make sure that this is also in AU. And the question told us that the orbital radius of Earth is 1.00 AU. So I'll just get to say this is 1.00 cubed. That's going to equal the orbital period of Saturn squared, so 10,759 squared, divided by the orbital radius of Saturn cubed, so RS3. Now to get RS3, or RS cubed I should say, all by itself, we just need to times by RS cubed on both sides. That's going to bring it up to the top on this left-hand side here, so RS cubed times 365 squared divided by 1.00 cubed equals 10,759 squared. Now, one thing you might also notice is we'd like to get rid of this 1.00 cubed, but 1.00 cubed is just 1. And if we're dividing by 1, really it's like this thing is doing nothing at all. So I'm just going to ignore it. Now, to get RS cubed all by itself, we just need to divide by 365 squared. So this means RS cubed equals 10,759 squared divided by 365 squared. This gives me RS cubed equals, if I punch this into my calculator, I get, 1 second, that gives me 868, so 868.8766. And then, of course, just to get the orbital radius of Saturn, we just need to cube root both sides of these. So orbital radius of Saturn, by cube rooting both sides to 3 sigdigs, is 9.54, and the units on that are AU. So again, we were able to kind of use like a long double fraction kind of method here, where we just set the Kepler's constant with Earth as the interest for our orbital focus, and Saturn equal to the other side. Both of these are orbiting around the Sun, so we can set them equal to each other and solve for missing information. So as long as two things are orbiting around the same object, you can set their orbital fractions equal to one another. Okay, so for the rest of the class, I want you working on the Keplers Laws and planetary motion worksheet that we're going to hand out here. If you haven't already completed it, make sure that your uniform circular motion vertical worksheet questions are completed already. Now, just another reminder, we have a circular motion quiz coming up on Tuesday, November 19th. We're going to cover the very last thing we need for that quiz during our next lesson. So again, I would suggest keeping this slide paused for the rest of the class here so you can refer back to it. And as always, if you ever have any questions, ask either anyone around you or give me a shout.